We've learned about 3 different types of intermolecular forces or between molecule forces. And so now we want to do some different problems to apply those concepts. So we're going to take a look at just a few examples here, and then we'll save some to do in class and to practice on your own. But the types of questions you might see related to these intermolecular forces. So you've got a list of molecules here, and it may help you to build some of them. I've got a few built here, or just watch my models. And we want to think through on each of them. Is it polar? Can I have hydrogen bonding, dipole-dipole, and dispersion between 2 or more molecules? Remember, all of these are intermolecular forces, so I've always got to have at least 2 molecules kind of in my head when I think about those. And then once we fill out this, we're going to draw some of those intermolecular force attractions. So first of all, let's think about, let's say CH4, okay? So CH4, the first thing I notice when I look at that is it's all CH bonds. And you should start to have this automatic thought when you see all C's and H's that those are all sharing electrons evenly. If they're sharing electrons evenly, it's not polar. So anything with C's and H's, if that's all it has, it's always nonpolar. Now, if you can think back to this sheet, there was one type of interaction that we saw for nonpolar molecules. And that was down here, these London dispersion forces, right? So that means that the only type of attraction I can have between 2 CH4 molecules is London dispersion forces. Let's just pop over here and say, hey, how could we draw that? So CH4 and another CH4, there's no molecular dipoles. So these were just kind of the 2 casual people walking through the grocery store, collide, say hi, and then never speak to each other again. It's a very weak attraction, and it is not tied to any large molecular dipole arrows. Okay, let's take a look at HF then, okay? You may have to draw these out as they get bigger. So HF, is this a polar molecule? Yeah, F pulls electrons, right? So here I would say, yes, this is polar. So now I need to think through, okay, let's think from the bottom up, what kind of attractions can it have? Dispersion. Everything has dispersion forces, right? Dipole-dipole, remember dipole-dipole was if I have a polar molecule, then if its twin is nearby, then yes, I can have that. So because this is polar, I can have a polar-polar or dipole-dipole attraction. And then finally, with the hydrogen bonding, I'm looking for OH, NH, FH in my molecule. So do I have that? I have that HF, so that would mean that yes, I can hydrogen bond here. There's space to sketch these up here. So here I might draw HF and another HF, and I want to be drawing those strong intermolecular force attractions. I could show this one in a couple of ways, but with hydrogen bonding, I'm going to tend to default to partial negative, always a partial positive on the H, the donor, and so that shows my hydrogen bonding. So let's try one more together. Here's another one with fluorine in it, and here you might need to back up and sketch out just a rough Lewis structure. You don't even need to count all your electrons exactly. I just know, oh yeah, carbon's always in the middle, the H's go around it, and fluorine would fill in there. So that would be a molecule, something like this, okay? If I'm looking at this kind of molecule, the C's and H's, those are all sharing electrons evenly. So C's and H's here, C's and H's here, those are the yellows, those are sharing electrons evenly. Fluorine, we know, is the most electronegative element on the table though, so fluorine is going to pull electrons really hard. So fluorine's pulling electrons hard. Let's say, is this a polar molecule? It is, because I've got that pink arrow, right? That means the same as polar molecule. Intermolecular forces from the bottom up. Do I have dispersion forces between 2 of these? Can they just randomly bump into each other? Absolutely, everything can, okay? Can I have a dipole-dipole attraction between the 2 of these? Indeed, I have pink and pink, so that means that these could line up where the fluorines say, hey, I'm pulling electrons and I'm pulling electrons, and let's be attracted to each other. Let's stick a bit. So yes, I can have this. Can I have hydrogen bonding? Well, I see F's and I see H's, so I need to look a little bit more closely at this molecule. Do I have an F that's connected directly to an H? And that's where you need to be able to sketch out this structure. Is my F directly connected to an H? It's not. And so what that means is the H's don't get positive like they do, like we saw here. So when H gets really positive, it's because it's connected to an O or an F or an N. These H's are connected to carbon and they're just happily sharing electrons with carbon. And so I do not have hydrogen bonding here. Even though I have an F, it's not connected to the H. So the H is not very positive and I don't get that extra strong attraction. All right, so what if I go to sketch this out? I can even keep these molecules kind of condensed. We did this on one of our early slides, CH3F. The F is pulling electrons, and I have that negative side attracted to the positive side. Those are going to stick together. I have intermolecular forces, and this is a dipole attraction. All right, so that is our first type of problems, or two types of problems that you might have to do. I've left you some gaps so you can practice them on your own.